everyone, in this video I'll be going over section 2.5, which is on continuity. I think you'll like this section maybe a little bit better than the last one just because it takes less prerequisite skills and I anticipate that it's a little bit quicker. Okay, so in terms of the prerequisites you need, what you essentially want to remember from previous courses is what continuity is. So typically in algebra, pre-calc, pre-calc 2, continuity is defined as when a function is defined, or we could say there are no breaks or holes in a graph. Usually we look at that a little bit more informally, and we might say something like something or a function is continuous if you can draw it, so draw the graph, without picking up your pencils. That would imply that there aren't breaks or holes. In calculus, we look at this a little bit more formally. So the calculus definition of continuity is that f is continuous at a point x equals a, if the value of f of x approaches f of a as x approaches a. In terms of notation, we would say a function is continuous if the limit as x goes to a of f of x is equivalent to f of a. Right? It's a little bit funky to understand that in terms of the calculus definition, but really all that's saying is, in layman's terms, if if the limit is equal to, so if the limit is equal to the point on the graph, then we know that the function is continuous at that point. So then the function is continuous at that point. All right, so what's really going on with this is, let's say we have a function, 2 lines right here. All right, we follow the function from both sides. They meet, they match up. You know, you don't have to pick up your pencil. There's no break there. You know that it's continuous. So the limit's approaching the same spot, right? And if they're exactly equal, meaning there's a filled in hole or a filled in point there, then you have something that's continuous. So we can use the concept of a limit to define continuity. All right, before we get into that specific definition even more, let's just make sure that we have the concept of what continuity is down. So we'll look at some more prereq type examples to get this concept and to help you remember interval notation if you don't remember it as of right now. All right, so in the following example, let's use this graph to list where the function is continuous and discontinuous. We're going to use interval notation when we do this. So first, let's just list the intervals of continuity, and this is where that interval notation will come in. All right, so I'm going to start by moving from left to right. Notice that this first circle here is filled in. That means the x value of -2 is included. So the first thing to note is that with the interval notation, okay, we're going to use the x values to create our intervals. Right, so let's go ahead and do that. Right, we're starting at x is -2, and that's included in the graph. There's a closed circle there. So we know from -2, as we follow this line, I don't have to pick up my pencil at all, so it's continuous there. However, when I get to x equals -1, I see there's a hole in a graph and there's a break in it. So there are 3 different kind of spots there. So this goes from -2 to 1. This is not continuous on -1, so not continuous at that point, -1. So let's start making a list for discontinuous, so where this is not continuous at. Okay, and that happens at x equals -1. That's because there's a hole and a break. One other quick thing to notice, and sometimes people make this mistake, is notice that if this circle right here is filled in, these two can't be. So you can't have a function if you have more than one y value for each x value. That's why it's essential that these other 2 holes are not filled in. Okay, back to the continuity part. All right, so follow that to -1. Notice it's discontinuous there. Right, now I'm going to go up to the next part of the function, and I notice when I follow this little curve here, that's continuous the whole time because I don't have to pick up my pencil. So there's a break at -1. This is how we denote the break. Now I'm going to go from -1 to, I see once I get to, this is x equals 1, once I get to where x equals 1, I have another break with this little asymptote here. So I have to stop that at 1. I have to put a parentheses because the 1 is not included in the area where this is continuous. Okay, so we have a break there. We'll put our little u, and notice that this will start back up at 1, but not including the 1. And now in this last little curve, I can draw without picking my pencil up, and then this arrow implies that it keeps going, so it remains defined or continuous for the rest of the x values. So that means we go to infinity. All right, a quick thing to note here is around infinity, I put a parentheses. The reason for that is I can't just stop at infinity. Infinity is not included. It doesn't stop at a specific number. Therefore, we use parentheses anytime that we have infinity or negative infinity. All right, so let's finish listing our discontinuous spots now. So we already got that there is a break at x equals -1, and then we saw there was a break at x equals 1. So now we have our intervals of continuity and the spots where our function is discontinuous. So this example is something that you might remember from previous classes. If not, we reviewed it. So just make sure that if it still doesn't make sense, you take a couple minutes to look it up. All right, so for the next example, we're going to do it somewhat informally with prereq stuff, but I'm going to start introducing the calculus aspects of it a little bit. For the subsequent examples, we'll do a more calculus-based approach. Okay, so let's use the following graph to answer questions A and B. All right, so we have our graph here. The first question is the graph continuous at x equals 1? So looking at x equals 1 right here, we can see that there's a hole in the graph. So we could answer this very informally and simply say no, because there is a hole in the graph. Right, so that would be the informal way to do this. If you wanted to use calculus to answer this, what you would have to do is look at that definition of continuity. So notice that from up here, a function is continuous if the limit that it approaches is equivalent to the y value or the f of value. So now if we go down here, we notice that calc-wise, okay, the limit as x goes to, and this specifies 1, so as x goes to 1 of my function, so f, and I'll just say f of x, is equal to, and now as I approach 1, I see from both sides, so from here and here, the function does in fact approach 1 point, and that's, I'll just say this is 1, that's where y is equal to 1. So I see that that limit does in fact exist. Oops. All right, so now that we've seen that, let's look at the other part of that continuity definition, and that's that the limit has to be equal to the f of value. So if we look at f of 1, we see that that is undefined. There's a hole there. There's not a definition for f of 1. Okay, so thinking about this formally, we can see that 1 is not equal to undefined. Right, going back to what needs to be true for continuity, we need the limit to equal that value. They're not equal, therefore this is not continuous. Not continuous. All right, so the next question asks us to look specifically at x equals -1. So now let's move over to the left and look at x equals -1. It asks, is the graph continuous at x equals -1? Think of the answer to that. And the answer would be no. No, it's not continuous. Okay, and that is because, since we have a break in the graph. All right, the next part of the question asks, does a limit exist at x equals -1? Well, this depends on the notation that you're considering, but remember when we discussed this in section 2.2, we decided that even if the function is going to infinity, as long as both sides are going to infinity, we will say the limit exists and that it's equivalent to infinity. So here we're going to say yes, each side of the function is approaching positive infinity, so the limit exists. Okay, so we can actually follow up with really parts A and B in this question. Okay, so following up, based on the results above, we'll say both. Is it true that if a function is not continuous, a limit does not exist? Okay, well, let's look at part A. We saw that the function was not continuous at 1 because there's a hole at 1. Okay, However, we saw that the limit did exist at 1, and that's because when we approached x equals 1 from each side, they went to the same y value, y equals 1, therefore the limit existed. Similarly, in 2b, we saw the function is not continuous because there's a break. However, since both the left and the right-hand side of the function approached infinity, where x was -1, the limit does exist. So a really common misconception or mistake that students make is they think, oh, it's not continuous, so the limit doesn't exist. That isn't true. You don't have to have continuity in order to have a limit. Okay, so I typed to conclude this, but essentially, no, that is not true. Even if there's a break or a hole in the graph, meaning the function is discontinuous, if our graph approaches the same place from the right and left, the limit does still exist. Okay, so I tied some calculus definition parts into this, but for the next examples, I'm going to use that definition even more specifically. All right, so example 3, let's use the definition of continuity and properties of a limit to show that the following function is continuous. All right, so if we scrolled up and looked at that definition again, which we have a couple of times, we should remember that we need to show that the limit as x approaches a of f of x must be equal to f of a for that limit to exist. Or in layman's terms, what this is, we need to find the limit as x goes to a of f of x and f of a. Okay, and then what we'll do after that is make sure they are equal. Right? If they're not, then that means that we have something that is not continuous. All right, so let's do it. All right, so I just noticed up here that I need to specify continuous at, and then let's use the value, add 2. I think that'll work well with this example. Okay, so continuous at a equals 2. A equals 2. All right, and I also noticed in here we put t's. It's really just the independent variable, but I guess I should have listed t's in my definitions here. Was trying to speak in general terms, but based on this question, we'd have a t there. Okay, so let's go ahead and explore a equals 2. Like we decided already, we need to calculate the limit. So we're going to find the limit as t goes to 2 of our f of x function, which is t squared plus 5t over 2 times t plus 1. From section 2.3 by the limit laws, we should see we can actually just go ahead and run this through. So running the 2 through the top part, we'd have a 2 squared plus 5 times 2. Running it through the bottom, we would have 2 times 2 plus 1. And this would end up getting us 14 over 5. All right, so we've calculated the limit. Now we need to find the f of value. So second part of this, let's find that function value at the same point. All right, so let's look at f of 2. Okay, so we simply plug that into our function to get 2 squared plus 5 times 2 over 2 times 2 plus 1. All right, we see this is also 14 over 5. Therefore, we have matched, or we have met that definition of continuity. So we see that f of a, aka f of 2, is equal to the limit as t approaches 2. Therefore, we do have continuity. Okay, so since equivalent, we have satisfied the definition. We have satisfied the definition of continuity. So the function is continuous at a equals 2. All right, so seems kind of obvious, but we are trying to prove this formally with a definition. Therefore, you need to show these two things are true, and we have in fact done that. All right, so the next example is somewhat similar, but it adds a different component of complexity. So what we're going to do is show that the function g of x equals x minus 1 over 3x plus 6 is continuous on the interval from -∞ to -2, not including the endpoints. All right, so we need to do the same thing. We need to use the definition of continuity to show this. The thing is, if you look, we have this whole interval. We don't just have a single value that we can plug in like we did in the previous example. So the question is, how do we handle it if we have an interval? What you do is you give this interval an arbitrary name. So what you have to do is give the interval an arbitrary name. Okay, so what I'm going to do is I'll just call it A. Let A be any value in the interval, and I'll just say in -infinity to -2. So this seems a little bit funky. It's kind of abstract, but you're essentially saying, okay, well, A can be any number on this interval. Therefore, if you show your two properties or your two things we showed in example 3 with A, then we know that this is going to hold true because A stands for any value on that interval. Now, I'm going to go through the same process that I did above. So I'm going to find the limit as x this time, because there's an x in that, as x approaches A, of x minus 1 over 3x plus 6 is equal to, now by the limit laws I can run the A through, so I get A minus 1 over 3a plus 6. Okay, next we need to check our function value and make sure that it matches the limit. So I'm going to take g of A. You can see if I run that through my function above, I get A minus 1 over 3 times A plus 6. All right, now we see that our function value is equivalent to the limit. Therefore, we can draw the conclusion that this is continuous. Okay, so this meets, or I'll say this satisfies, I'm spelling that wrong, I believe, satisfies the definition of continuity. Therefore, g of x is continuous at x equals a, where a is any number in the interval, I'll just say in -infinity to -2. Okay, so a little bit abstract in that you have to name A to be in that interval, but once you're able to do that, the process is the same as what we did in example 3.